Hello students, myself Welcome to Process Control Lecture Series. In my previous lecture, I completed chapter number 5. In that chapter, we discussed about the different control modes. That means proportional mode, integral mode and derivative control mode. Then after we discussed the composite control mode like PI mode, PD mode, that means proportional plus derivative mode, proportional plus integrative mode, and PID mode, that means proportional plus integral plus derivative mode. Then after we discuss about the analog controller. Now in this lecture we start new chapter, and in this chapter we learn about the controller tuning. So in this lecture, first we study about the tuning of controller. Then we discuss about the design problems, that means which are the problems occur during the designing of the controller. Then after we discuss about the performance criteria, and last we discuss about the time integral performance criteria. So in this lecture we discuss about this thing. So now we start. So first one question come in our mind: why study controller tuning? That means why we study tuning of controller or controller tuning? So the answer is controller tuning refers to the adjustment in the tuning parameters. That means proportional gain, integral gain and derivative gain, in order to ensure the best response of the controller. In any controller process, when a controller is properly tuned, there is reduced process variability, maximum efficiency and minimum energy cost and high production rate. That's why, or we can say hence, it is important to study controller tuning. So that's why we study the controller tuning. That means in the process, when controller is properly tuned, that means what? We adjust our output so we get exactly desired output. So if we tune the controller, then we reduce the process variability, then we can increase the efficiency and minimum energy cost is required. So this is the advantage of controller tuning, or we can say in other words, that's why we tune the controller. So this is the importance of controller tuning, and that's why we study this chapter. Now we discuss about some designing problem. So which are that? So here consider the block diagram of general closed loop system shown in figure. That means this is the general diagram with the control system. That means here feedback control system is used. You can see here we use the controller to control the system, and how it works I explained in this diagram. So when the load or the set point change, the response of the process deviates and the controller tries to bring the output close to the desired set point. So this is the simple principle or working of this closed loop system. That means if there is some change in the load, or due to that load change the deviation is occurred, that means the set point is changed, so the response of the process is deviated and the controller tries to bring the output close to the desired set point, or we can say it try to deviation 0. So this is the simple procedure of this working of the closed loop system. Now figure here show the response of the control process to until the step change in the load when the different type of controller have been used. That means in the previous slide that I have given example of the feedback control system. Now we control that system by using different controller. That means we use a proportional controller, PI controller and PID controller. And how it works we can see in this diagram. That means the response of controller we can understand by using this figure. We notice that the different controller have different impact on the response of the controller process. Thus, the few design questions arise. So which are that question? The first one question come in our mind is what type of feedback controller should we use to control a given process? That means which controller we use. That means P controller use, I controller use, or D controller we use, or we can say composite controller can be used like a PI controller, PD controller, PID controller. Which controller is best for the controlling of the system? So this is the first one question or the challenging question for our. Then the next one question come in our mind. How do we select the best value for the adjustable parameter of feedback controller? That means this is the part of tuning. So how we select the best value for the adjustable parameter by using tuning. So this is the second one problem. And the last one is what the performance criteria should we use for the selection and the tuning of the controller. So these are the some problem, or we can say some question arise when we design a controller or a control system. So let us now study the question above in more detail and provide the initial guideline for the design of the feedback controller. So now we study this question in more detail. So first we understand the performance criteria. So here you can see the block diagram, or we can say consider two different feedback control systems providing the two closed loop response shown in figure. That means here the two control system, first one is the A and second one is control system is B, and they provide the control response accordingly shown in the figure. The response A has reached the desired level of operation faster than the response B. Now we can see in the figure here, by figure we can understand the response A has reached the desired level of the operation faster as compared to the response B. Now, if our criteria for the design of the controller had been, now our criteria, first one criteria is what? To return to the desired level of the operation as soon as possible. So, at that time, then we would select the controller which give the closed loop response. That means we choose the type A response. That means type A controller we choose. Now our criteria is changed. Now our criteria is to keep the maximum deviation as small as possible. So this is our another criteria, or our criteria is changed, or we can say the return to the desired level of the operation and stay close to it in a shorter time. So at that time we had to change our controller. That means we would select the other controller yielding the closed loop response of type B. So according to our criteria change, we have to change the controller. So this is the performance criteria. Now for every process control application, we can distinguish accordingly steady state performance criteria, and second one is the dynamic response performance criteria. The principal steady state performance criterion usually is zero error at steady state, and the evaluation of dynamic performance of closed loop system is based on two types of commonly used criteria, which are that first one is criteria that use only a few points of response. They are simple but only approximate. And second one is criteria that use the entire closed loop response from the time t is equals to 0 till or until the time t is equals to very large. That these are more precise but also more consumption to use. So the performance criteria are based on some characteristics features, which are that. So first one is overshoot. We already know what is overshoot. Then second one is the rise time. Like rise time is what? The time need for the response to reach the desired value for the first time. So this is called the rise time. Then after settling time, the time need for the response to settle within the 5 plus or minus 5% of desired value. Then after the decay ratio, that means decay ratio is the responsible trade-off between a first rise time and a reasonable settling time. And the last one is frequency of oscillation of the transient. So these are the performance criteria of the system. So we have to consider this performance criteria, and according to we have to choose the controller or tune the performance. So now we discussed about the time integral performance criteria. The shape of complete closed loop response from time t is equals to 0 to until steady state has been reached could be used for the formulation of a dynamic performance criteria. Unlike the simple criteria that use only isolated characteristic of the dynamic response, that means we discussed criteria in the previous slide. The criteria of this category are based on the entire response of the process. That means we discussed criteria like the rise time and settling time is a simple criteria that use only the isolated characteristic of the dynamic response. The criteria of this category are based on the entire response of the process. That means the time integral performance criteria is based on the entire response of the process. So which are that? The first one is the integral of the square error, and we can define as ISE, and the equation is for the integration from 0 to infinite eta square t dt. Here is eta is indicate the error. Now the next one is the integral of the absolute value of the error, and it is denoted as AIAE, and it is defined as integration 0 to infinite eta t dt. And last one, time integral performance criteria is integral of the time with absolute error, that means ITAT, and it is defined as 0 to infinite t modulo eta t dt. So this is the time integral performance criteria. Now we discuss general about this time integral criteria. So if we want to strongly suppress the long error, ISE is better than IKE because the errors are square and thus contribute more to the value of the integral. Now, for the suppression of small error, IAE is better than ISE because when we square small number, they become even smaller. Then last one is to suppress error that persists for a long time. The IATA criteria will tune the controller better because the presence of a large T amplifies the effect of even small error in the value of the integral. So this is the general discussion about the time integral performance criteria. So in this lecture, we study about the tuning of controller. In that we study the design problems. Then we discuss about the performance criteria. Then we discuss about the time integral performance criteria. Thank you.